which equals what is that line integration of this vector field around this closed curve. This is what Stokes theorem says. So I think this will be clear to you if you look at this surface. Here, the question here is to verify Stokes theorem for this particular vector field, and where S, the surface under consideration, is the upper half of the sphere given by this. This is the equation of a sphere, x square plus y square plus z square equal to 1. This is a sphere of radius 1, right? This is a sphere of radius 1. X square plus y square plus z square equal to 1 is sphere of radius 1. So S is the upper half of the sphere, means something like this. See, upper half of the sphere S, this is something like this, and C is its boundary. So the boundary here is, the boundary of this surface here is a circle on the xy plane. The boundary here is a circle on xy plane. Okay, so what is the equation of this circle? The equation of this circle is going to be x square plus y square equal to 1. So because on xy plane z is 0, right? So the equation of the circle on xy plane, or the curve, which is the boundary of the surface under consideration, is a circle of radius 1, x square plus y square equal to 1. All right, so here you find that unit vector k cap is pointing along the z-axis, and unit outward vector, whenever we consider surface element over here, ds, ds vector will be ds into unit outward vector. N cap is unit outward vector. Unit outward vector means a unit vector or a vector having unit magnitude pointing away from the surface, So if you consider ds vector here, ds element, surface element over here, unit outward vector will be something like this. Unit vector which is pointing outward from the unit normal vector. In fact, this is unit normal vector. Normal means this vector is at 90 degree to the surface here. All right. Now, so the boundary of surface as a circular radius, this I have discussed. Right. So what is the line element? Line element in general, line element dr here, over here, what you have to do is, in order to like integrate over this curve C here, you have to consider a line element dr. So dr vector is in general, this is dxi, dyj, dzk. Okay, because r vector, position vector, we write it as xi plus yj in Cartesian system. This is your r vector. So dr vector will be dxi dyj plus dzk. So as simple as that. Now you can consider this, and now you take the a dot dr, because you are going to execute left hand side is a dot dr vector, this along the curve. This is the left hand side of your Stokes theorem. So you take a dot product of a with your dr vector. Okay, and also you should know that over here, as I said here, as you perform this loop integration, a dot dr, you have to perform this loop integration along this line, along this curve, which is bounding the surface under consideration. So along this curve, since as I have said here, a curve, the curve under consideration is lying on the xy plane. So along this curve, z value is 0, right? So because of that, when you, after taking the a dot dr, you just put z as 0 along the curve, z value is 0. All right. So if z is 0, a dot dr reduced to this, and you just use in terms of theta, x as r cos theta, and here your radius is 1, so xy as r sin theta, your radius is 1. Then this integration of a dot dr along the circle on the XY plane will be reduced to this. Okay, and because your line element here, your line element, where is that? Yeah, this will reduce to that. A dot dr over here reduces to this, right? A dot dr reduces to this. So this is dx. X is r cos theta, means x is r cos theta, means your dx is r differentiation of cos theta is minus of sine theta d theta. Okay, so dx will be minus of r sine theta d theta. Your r is 1, means your dx is minus of sine theta d theta. So if you just put that over here, we perform the remaining integration. So this is a simple, I think, trigonometric calculus. So you just perform the integration of this 2 sine theta cos theta is sine 2 theta. So use your trigonometry knowledge and your calculus knowledge to perform the integration. So sine 2 theta integration equals cos 2 theta upon 2, like that. So if you continue, eventually you will get pi, right? And just a minute. Yeah. Okay. So here the right hand side of this Stokes theorem is surface integration of curl of A. So you have to perform the curl of A. Curl of A is this. This is how we perform curl of A. I've given you an example also. Curl of A is this I have explained. So you perform the curl of A, eventually you will get K cap. So this should not be a problem. So I cap coefficient will be differentiation of y square minus of y square z with respect to y, that is minus of 2yz minus differentiation of this quantity with respect to z, that will be minus of 2yz. So minus and minus cancels out plus. So like that, if you do that, this is what you're going to get, curl of A. And here this will be curl of A dot n cap ds. And you know that this curl of A is k cap. You have calculated this curl of A as k cap. Right. So here this will be k cap dot n cap ds. So this will be simply a projection of n ds vector on the xy plane. Okay. So what I mean by the projection here is that, say, this is k cap is along the x-axis, and let's say if you consider any surface element here, this is your n cap. So n cap dot k cap will be, this is theta. So n cap dot k cap will be cos theta, because the magnitude of both n cap and k cap are 1. So cos theta. So if you have a surface ds here, so what you're going to have here is that ds n cap dot k cap will result in cos theta ds. So if you have a surface ds over here, cos theta ds will be a projection of this surface on the xy plane. A projection of this surface on the xy plane. So this will be your ds cos theta. So it's something like this. Just a minute. Let me. So let's say you have a vector A here, and let's say you have this exists as your y-axis. So this is j cap. So if you perform A dot j cap, A vector dot j cap, this will be magnitude of A, and j cap magnitude is 1, and cosine of the angle between them, this is your cos theta. So magnitude of j cap is 1. So this is magnitude of A cos theta. What is this magnitude of A cos theta? This will be, if you drop a perpendicular here, this segment, this is your projection here. This is the magnitude of A cos theta, right? So similar to that, if you define something like this, this is, let's say, your x, this is, let's say, your y, this is, let's say, your z, and let's say you have a certain surface, for example, surface which is a little bit inclined, something like this. Okay, whatever may be the surface. So this is your ds, and when you write your ds vector, this is the magnitude upon n cap, this is the direction of n cap, right? So along this z-axis, the direction unit vector is k cap here. So if you take a dot product here, what is that? K cap with ds vector, this will be k cap dot ds n cap, and if the angle between them is theta here, this is going to result in k cap dot n cap will be magnitude of both of these vectors are 1. So the angle between them is theta, theta means cos theta, right? So it will result in ds cos theta. So what is ds cos theta? If this is your ds here, ds cos theta will be projection of this surface on your xy plane. Okay, projection of this surface on your xy plane is your ds cos theta. Okay, so if that is the case, then on the xy plane, the area element will be dx dy. Okay, on the xy plane, you have your area element ds. On the xy plane, the projection of ds on the xy plane will be, the element will be dx dy, because I think I have convinced you that on the xy plane, like when we consider z equal to 0 plane and z equal to 3 plane, so we have discussed that the real element on such plane, that is xy plane or any plane parallel to the xy plane, the real element will be dx dy. That was what I have discussed before. So if you recall that, we can write this as a dx dy. And now, since the surface integrate, the surface has to be performed, integration has to be performed over this now, because this is on the xy plane now. So instead of having the whole x squared plus y squared plus z squared equal to 1, we have projected our surface on the xy plane because of the dot product with k cap here. So we have to follow this, right? So in this surface integration, instead of this, we write dx dy, and here the limit will have to be chosen according to this, which says that y square is equal to 1 minus x square, or y is equal to square root of plus or minus 1 minus x square. So you perform the integration from minus square root of this to the plus of this, and then you have to perform x from the radius, the back side of the radius, that is x equal to minus 1, x equal to 1. So you perform that integration, and if you do that, say moreover, whatever function you're having here, it is constant, right? So you can consider this as an odd function. So this integration from this to this, like minus a to a, can be written as 2 times 0 to a, so 2 times y equal to 0 to this. So you perform that integration, and this is what you have. And then after that, you have this. So this is again an even function. If this is an even function, if you just put f of minus x here, minus x square is this, and same as f of x. So even function means minus 1 to plus 1, you just convert into 0 to 1, so 2 2, and eventually if you put using simplify this integration using this calculus, that is, sorry, trigonometric property, you will eventually find this as pi. Okay, so this will be exactly same as that. So that's how we do it. So I will provide you the notes also, anyway. So quickly I will go through this. I think how much time we have spent. Yeah, we have spent around 35 minutes. Only for a few more minutes. So this is another vector integration theorem. So this is called Green's theorem. So as I said before, in Stokes theorem, we are considering an open surface, which may be flat or which may be curved also. As we just discussed, we are considering a sphere which is cut into half. So that was a curved surface bounded by a circle on the xy plane. That was what we discussed in the case of Stokes theorem. So we are considering some sort of curved surface bounded by a curve right? So, but Green's theorem is valid on only for plane. So here we are considering R as any region on the xy plane, right? So this is, let's say, x axis. Let's say this is your y axis. So you consider any region R, flat region R on the xy plane, right? On the xy plane means this is flat plane, flat surface, bounded by a simple closed curve C, right? So then what it says is that then if m and n are continuous functions of x and y having continuous derivatives within this region R, then the Green's theorem says that loop integration, so loop integration, there has to be a symbol like this, loop integration of m dx plus n dy equals surface integration over this region, that is surface integration over this region del n upon del x minus del m upon del y, where C is the loop which traverses in the counterclockwise direction. So counterclockwise direction, C is counterclockwise, it is rotating like this, counterclockwise. So here again, the surface element here is written as dx dy, because we are considering a region on the xy plane. So any infinitesimally small surface over this can be represented using small segment along x multiplied with small segment along y. So dx dy. Okay. So let's quickly go through this, and then we can stop. I think I can finish this in about 5 minutes, because I think once you follow the previous two calculations, this should not be a problem. So verify Green's theorem for this, where C is the closed curve of the region bounded by y equal to x and y equal to x square. So y equal to x is what is y equal to x? Let's say this is your x axis, this is your y axis. Y equal to x is just a straight line like this. So for like if x is 2, y is also 2, so it is y equal to x. If x is 4, y is also 4. If x is 5, y is also 5. So this is y equal to x. If x is 6, y is also 6, like this. All right, so it will be a straight line like that. Now and here when you consider y equal to x means y equal to x as equation of a line, then this angle will be at 45 degree, because x value is always equal to y. That means this angle will be at 45 degree here. All right, now you have another curve, another line here. This y equal to x is extending up to this, something like this, y equal to x. The equation y equal to x, sorry, the line y equal to x will be extended from this infinity up to infinity, right? Now what is y equal to x square? Y equal to x square here at x equal to 0, y value is 0, x equal to 0 0.1, y value is x square means 0 0.1 square, this will be 0 0.01, x equal to 0 0.2, y value is 0 0.2 square means 2 to the power 2 is 4.04. So when x value is 0 0.9, y value will be 0 0.9 square, that will be 9 times 9 will be what is that, 81, right? So 81, so there is a decimal point, this will be 0.81. But when x is 1, y will be 1 square will be 1. When x is 2, y will be 2 square, that is 4. When x is 3, y will be 3 square, that will be 9. So if you follow that, this will represent something like this. This will represent, let's say this is your xy And let's say you start with this here. This will represent something like this. This is, let's say, 1. This is, let's say, 1. So this was your y equal to x line. Now y equal to x square line will follow something like this. It will follow something like this. When x value is this is 1, x value is less than 1. When x value is less than 1, if you see that x equal to 0.1, y is 0.01, 0.2, 0.04, 0.9, 0.81. So when x value is less than 1, then in that case, y value will be less than x. But when x value is greater than 1, y value becomes x equal to 2 means y is 4, x equal to 3 means y is 9. So your line, your curve will be this. This is y equal to x square. I hope you can picture that. Now, we are considering a region bounded by this two line. So this is one line, y equal to x. This is another curve, y equal to x square. So the region bounded by these two will be this region. This is the region under consideration here for our problem. Okay. So this is the region we are going to consider R. And we are going to consider counterclockwise. Right, counterclockwise means rotating in the anticlockwise direction. So we have to perform the integration from this to this along this line and then come back to this point. So that is the loop integration that we are going to consider here. Okay, the loop integration, this loop integration has to go in the counterclockwise direction. All right. So just 1 minute. I almost finished. Just 1 minute, I have to forward one message. Okay, so this is m in this case, n will be x squared, so you can just write it like that, and you have to perform the integration over this closed loop, almost over. Okay, so I will not take much time now. So we can divide into two segments, one along this curve. This curve is defined, the curve which is defined by y equal to x squared. Along the curve defined by y equal to x squared, we write it as C1 curve. And we can divide another curve along which we have to integrate is along another line, is from this point to this point. From this point to this point, it will travel along y equal to x. Right, it will travel along y equal to x line. So the complete loop integration, that is C here, can be divided into two segments, one C1, from this to this, another C2. Right. So as you travel along from this point to this point along y equal to x squared, the x value will change from 0 to 1. And from this to this, you are coming back, x value will go from 1 to 0, like this. Okay. Because here along C1, you are going to write, along C1, the equation of the curve is y is x squared. Y is equal to x squared, and the x limit goes from 0 to 1. So for m, you just put for m in place of y, you just put x squared. In place of y, you just put x squared. So this is what you are going to get. All right. So your dy also here in this case, y equal to x squared means your dy will be 2x dx. Okay, 2x dx. So if you perform this simple integration, you should be able to arrive at this. Okay, So perform the integration. This is what you're going to get. And I think just simple integration with the limit. This is finally what you're going to get. Now along C2, first we are traveling along your C1 here. This is your C1, that is the equation here is y equal to x square, and we have arrived at this point. From this we are traveling back to this along this line. So the equation of this line is y equal to x. So yeah, along this line, instead of y you just put x, instead of y you just put x. This is what we're going to get. The integration limit is from 1 to 0. So if you do that, this is what you're going to get. And yeah, the whole integration will be here. Out here you get -1. This will be 19 upon 20 minus 1. So this is what you will get. Now integration over the region. Just 1 minute. Just 1 minute. What is that? Oh, collaboration with back university. Resource collaboration. Resource collaboration with Uzbek University. DST sponsored project. Okay, I hope that answers his question. Now integration over the region. So again, the right hand side is simple. N value M value for a given problem. So you just differentiate. N value is x square, M value is this. So you just differentiate. This is what you're going to get. And if you do this, then this is what you're going to get. And here dx dy. So you have to integrate along this line for the y and x value going from 0 to 1. So simply you will get this result. Okay, so if you perform that, the reason here we are going to integrate over this is that say you are going to perform integration with x and y, and what we are having here is that this axis is y, this is your x axis, and this curve is defined by y equal to x square, and this line is defined by y equal to x. So you just take a limit of y from this y equal to x square to y equal to x. So along this line, and you travel x from 0 to 1. This is 1 1. X value is 1. You travel x from 0 to 1. So that way you can perform integration over this region. Okay, if you do that, you will get the same thing, and that verifies your Green's theorem. So this is your assignment. You can calculate this. All right, I will stop. So I will upload this video once I reduce the size. So if you type your attendance, you can exit the meeting. No more class this week, so hopefully I can take 2 more class next week, and there we can start curvilinear coordinates. Okay, good night everyone. Type your attendance and exit the meeting. All right, I think I can exit the meeting now. Everyone has type attendance.